Good afternoon, everyone. We're just waiting for a few people to join, and then we'll get started with the session this afternoon. Louise, are we ready to start yet?
Yes, go ahead.
Okay. Good afternoon, everyone. This is the first in a series of webinars that we're going to be doing regarding DEFORM software, generally talking about manufacturing process modeling with DEFORM. And today we're going to be covering just an overview of the system. We'll give an introduction to wild analysis and PDS vision, talk about why we use simulation, talk about the DEFORM system, run through some application examples, and then we'll have a Q&A at the end. Just a bit of housekeeping for the session. The participants are going to be muted during that, but if you have any questions, please use the chat panel, and then we'll do a Q&A at the end and answer some of the questions. This session is going to be recorded, or is being recorded, and we'll make the presentations available at the end for those that want them. As I said, this is going to be the initial overview of the DEFORM system, and then we're going to go into some more detail in subsequent webinars on hot forging, cold forming, heat treatment, machining and joining technologies, which will also cover some more advanced applications as well. So I'll get started now. Hopefully many of you know about Wild Analysis. We've been around since 1980. We're based in Manchester, and we've got clients all across Europe. We provide CAE systems and solutions, consulting, training, software, and technical support for applications, as well as functional safety and reliability services. We've got a large team of in-house consultants, and we've recently become part of PDS Vision, who are a digital transformation company based initially in the Nordics, but now a global company. And we have 3,000 customers worldwide. They specialize, or we specialize in 3D design, CAD, product lifecycle management, PDM, simulation technology, Internet of Things, augmented reality, and associated aftermarket solutions. So we're in the process of integrating with PDS Vision at the moment, and it's been quite successful, and it's exciting for the future. So you'll see a lot more PDS Vision type branded material from us, and if you look on our website, you'll see the updates on there. From the wild analysis perspective, we cover a range of sort of software applications, including DEFORM, ReliSoft, ANSYS, MoldX. So on the manufacturing side, we look after DEFORM and ANSYS, and today we'll focus obviously on the DEFORM software. When we look at why people use DEFORM and where DEFORM will be used, traditionally metal forming design and development has been used on trial and error. Expertise can take years to develop, and that expertise gets lost as people start to retire, and we bring in new engineers, and we want to sort of share that knowledge and bring that process along. And often processes that are existing or legacy processes and products might be acceptable in production as we change material due to regulation changes or supplier issues. These can be those acceptable processes can be maybe not ideal, and they're not certainly optimized. And when you're bringing new products to market for challenging parts using new materials and aggressive processes, these old sort of techniques of trial and error are really non-competitive in today's market. So using simulation up front can really help. So simulation, ideally, if we look at a trial, a previous way of manufacturing design, you do the engineering up front, maybe you do some die manufacturing, do some shop trials, and then inspect the parts. Using that system, you don't really get any feedback on that initial design and engineering right until the end of the process, where you've invested a lot of cost in the process. So doing upfront design allows you to bring that knowledge up front and understand the process and get design feedback at a much earlier stage. And right, using simulation tools right across the board in terms of that upfront design, especially in manufacturing, can be a big benefit that allows us to go to trial runs much more successfully and get right first time. So the tools that we're going to talk about today will enable users to have those virtual trial runs prior to making any tools or parts, to understand the material flow, the residual stress, possibly the microstructure, and look at how these products will perform in service. So you can run the tryouts on the computer in some sort of system. You can look at more detailed results in terms of the hidden behavior, what's going on inside the material. You can get that feedback really early on, and you can troubleshoot the process and the product. And hopefully this will enable you to have much more successful trials for your manufacturing process. The DEFORM system itself is a multi-physics modeling environment. So we are primarily looking at, for most cases, looking at the deformation of a material. And when you heat the material up, we're also looking at the, if you're doing hot, warm forging, then we've got the thermal aspects as well. So we're looking at thermal expansion and adiabatic heating. So we've got this coupled simulation approach, which looks at the thermomechanical response of the material. In terms of heating the material up, we might do that using another method such as induction heating or resistance heating. So we have a coupled ohm loss calculator, so for resistance heating, or boundary element codes for induction heating. And taking the sort of simulation further into multi-physics, we can start looking at things like phase transformation, recrystallization, grain growth. So all of this can be run in a fully coupled simulation. And we're really interested in the flow stress of the material, how the material is going to respond to things like temperature change and the rate of deformation. And that's the sort of core functionality of the DEFORM system. And when we apply these kind of applications, we're really trying to look at what's happening to the material across the whole process chain. So we might start from initial primary processing applications such as cogging or rolling or extrusion, and then look at secondary applications as forging, and go through possibly, I've got cold forming applications like drawing or coining or spinning applications. Following on from that, you may want to do some heat treatment, whether that be in a furnace module or local heat treatment with induction heating or resistance heating, to look at the products. And then we may join this through some technology, whether we use solid state or welding applications, such as friction stir welding or linear friction welding. And components need to be machined as well to final shape, so we might look at that. And Throughout this process, we've developed the shape of the material, but we've also developed the residual stress in the material. So there may be some residual stresses in the part. So when we machine them, they potentially might distort. So we want to understand machining distortion. And once you've got your final machine product, you want to put it in service and understand how the residual stress and microstructure will affect the lifing. So the DEFORM system is built to try and understand that process throughout the product throughout the whole process chain. We don't simulate the casting itself. We can do solidification, but really anything in between those processes, between the in-service application and the primary processing, are sort of target applications for DEFORM in the world of metals. So we'll talk about how the system is set up, where we have modules specifically to model these applications as a general overview, and then in the subsequent webinars we'll go into some of the drill down into a lot of the detail of these. But DEFORM offers a integrated process modeling system with using a multi-operation interface for cold, warm, hot forming kind of applications. There's also a general purpose pre-post, so if it's not a forming application, it may be just a stress deformation or anything with a very large deformation of material we can handle in DEFORM. The system's very mature now. It's powerful, easy to use. We can do very detailed, accurate simulations, and it's employed by many manufacturers and material manufacturers globally. So we'll look at some examples and some case studies of where they are applied. Typical predictive capabilities that you get with DEFORM will be looking at understanding the material flow during a forming process to see whether we fill the cavity or fill the die or reach the desired target shape in an open die kind of application. We may want to understand whether we get lubrication or gas traps in the system so that we can design our tooling correctly, so we can understand the material flow so we're not getting folds or pockets. We may want to troubleshoot defects and understand whether we're going to get folds or laps or subsurface defects in there, so being able to track the material flow and tools in there to be able to determine if that's the case are readily available, and those include sort of flow defects. Also, very typically, we want to understand forming loads in the process to see whether it will work on a particular a machine with a given set of process equipment that you might have at your disposal. So understanding those loads is quite important to designing the processes. Other applications, we might want to understand whether we're going to get any damage in the material or fracture. Perhaps it's part of the process to shear a material, but also if you're doing more advanced drawing applications, understanding fracture limitations, quite important. And everything that touches the material is going to have a stress in there due to the pressures in the system. So understanding die deflection, die stress, insert fracture of cold forming, very key applications. And when we look at some of these applications for DEFORM, we've got a range of tools that allow our different users to be able to look at different things. So we have an entry-level system, which we'll talk about in a second, which is more aimed at the designers, which will be typically looking at die fill, lapse, flash, load, and die failure, and they're very easy to use, very simple systems. As we start moving up towards the complexity of simulation to understand things like microstructure, machining distortion, and heat treatment, there's a bit more onus on the user to be understanding the FEM and the detailed mechanics of the process that are going on. So with that respect, we have for targeting the designers, we have some products called Forming Express, which are available in 2D and 3D, very easy to use systems, very quick to set up, and they're true vertical applications for forming processes. But as we move over to more complex things where people perhaps are doing research and PhDs, people go into the more open system and using the modules that are at the disposal. So we have a range of templates that are application specific for certain applications, and I'll talk about those in a second. And then some additional modules that people might want to apply specifically to those applications. And extending those further, we have tools like design of experiments, DOE, optimization, and now data analytics, and I think even some neural networks in the latest system, which will allow very advanced analysis and predictive capability for applications. So just looking at a few simple cases, here's a simple cartridge case with a multiple application. These are kind of DEFORM 2D simulations that have been done for many years, looking at multiple operations of deep drawing. And we want to understand the fracture, the thickness, we want to understand strain hardening, loads on the tool, die stress. So it's a nice example of a complex process that we can handle quite simply with the system. Another typical hot forging application would be a multi-stage operation where we start with a billet, develop a preform through some rolled applications, and then a three-stage forging process in this case. So here's the initial rolled preform case. So we're moving the material to the outside, and then we go through a bend and some hammer forging processes and the multi-blow hammer operations to get to the final form. So again, we're doing this throughout in the multi-operation system, and there'll be a demonstration of the MO system of how it works shortly. But essentially, when we look at this is a process where we might have a two-stage operation for an aluminium wheel. So if we look at how the process is set up, we have an initial billet in the furnace. It goes through we rest it on the tool, and it has an upset load. It has a forging, and then we unload the tooling. It's transferred, so there's a transfer time there. Then we have a finisher, so it rests on the tools. We do the forging operation. We open the tools, and then we eject it. So we can set up in the system an operation for each of these. These ones here that we see with the forging icon, these are actual deformation operations, and the rest of them are essentially heat transfer operations. So we want to track the evolution of the temperature during the whole process, so we can break this up into the separate operations so that we can look at these all individually, and that will allow us to go through and optimize and develop the process as we want to change the design throughout the system. So here we can see this in process. So we have the initial heat up with the furnace, we transfer through the forging operation, it rests on the tool, we take it to a finishing operation, do the forging, open the tooling. It's a bit quick, that video, but I'll just run it again. So the DEFORM system allows us to set up these multiple operation applications so that we can delve in and modify each one separately. And once we have this set up as a process chain, we can save that as a template, so you can develop your own bespoke template for your particular operation. So the system itself, we have the entry-level designer tools called Forming Express. There's some modules you can add on parallel processing or batch queues for these applications. As we move up to the engineer analyst level, we have the DEFORM 2D and 3D products, which come with a range of application templates for forming, machining, cogging. I'll show some examples of those. And there's some additional modules that you can add to that system, such as microstructure, DOE optimization, data analytics, material suite, furnace modeling. And we have a system called DEFORM Premier, which wraps all of those into one bundled product where you get every bit of the capability. In addition, there's some standalone products for certain applications that include a full post and simulation capabilities, such as for ring rolling, we have a standalone furnace module, and we have a standalone system called DEFORM HT 2 and 3, which are for heat treatment modeling. So effectively, that's the same as using DEFORM 2D or 3D and adding a microstructure module, but without the large deformation. So if you're not interested in large deformation, just the heat treatment, then the HT, the heat treatment system is very good for that. The application templates themselves, we have a forming template, which is good for general forming applications. So here's an example of a hip implant multi-operation. This would be applicable to do in either the DEFORM F3 or the DEFORM 3 type simulation. In terms of material supply or pre-processing prior to applications like ring rolling, we have an open die system, which you can combine with the forming templates here to maybe look at making preforms, and then using open die operations to develop those into a larger ring. So this would be perhaps be developing a preform for a ring rolling application. You go through many operations to this. So we can use the open die or cogging module to set up a sequence of perhaps hundreds of operations and combine these into a full process. Then we have applications for machining in 2D and 3D, to look at machining cutting so that we can understand the surface integrity, residual stress, perhaps microstructure in the surface as well. So understanding cutting forces and chip morphology and the temperature in the tool and tool stress as well. So it's quite an advanced system there. We have a module for extrusion, specifically looking at Lagrangian 3D extrusion to look at the breakout loads and how the material flows out of the dies. But we also have a steady state simulation and an ALE solution to look at those steady state processes for extrusion. And again, so it's looking at folds, laps, it's looking at weld lines and die stress in that application as well. We have a module for ring rolling, which looks at takes that preformed shape that we made in open die and then looks in this case to look at a casing application here. So that's a bespoke module, and that uses a very specific solver. So there's a dedicated solver for ring rolling. And then we have a module for shape rolling. So shape rolling, we can either do similar to the extrusion, we have a Lagrangian solution, but we also have steady state processes for continuous rolling, for plate, sheet, bar, for long products as well. And we also have a 2.5D system, which is very fast at predicting material shape for all the processes. So a couple of other modules that are more recent in DEFORM, we have a new spinning and flow forming module. So this allows you to set up sequences of multiple passes for either spinning, flow forming kind of applications. There's also a tube piercing module in that one as well. Spinning processes are quite challenging, so that's a very interesting module. And then more recently, in the latest version, we have a new welding module which is available. So it builds on the technology that we've got in DEFORM for additive type applications to allow sequential simulations for automatically modeling the weld path and the heat source and adding the material. And we're interested in looking at residual stress and distortions in the process for that. So that's something that we'll talk about in another application. Yeah, microstructure module, we can look at phase transformation, heat treatment applications. We're going to do another detailed webinar about that, but looking at phase transformations for steels, looking at things like diffusion, predicting hardness, predicting martensite. And then there's a microstructure module where we can look at different length scales, whether we're looking at component scale or finite element scale, to predict phase transformation, maybe grain size, precipitation, recrystallization, those kind of effects. So we'll talk about that in more detail. And extending that further, there's a material suite in DEFORM, which you can use to look at things like voids and inclusions and crystal plasticity and texture. And there's a new CA cellular automata model in DEFORM. So that sort of covers the whole system and the capabilities there as an overview. It's kind of a brief overview. So there's a lot of capability that we'll hopefully touch a lot more on in the future. But now I'm going to pass over to Thomas, who's going to give a demonstration of the system. Over to you, Thomas.
Hello everyone. Yeah, my name's Thomas. I work in the technical team, specialising in DEFORM, and so I've prepared just a short demonstration of a setup of a forging express process. So I'll just share my screen and play that. In this demonstration, we'll look at the 3 stages to form a combination spanner. So we're looking at a transfer from the furnace, a flattening operation, and a forging operation. So here we are in the DEFORM software. So the first thing to do once we open this up is to create a new project by clicking the new project icon. This we're going to call spanner, and the location will be in your default working directory. Normally that's in your user directory, your Windows user directory. We're creating a new project and we want the first operation to be the heat transfer. Now that's particularly simple, so we're just going to have that move from a furnace through air for 5 seconds. So we can use this heat transfer express operation, which just simplifies the inputs needed. And for the unit system, we're going to use the metric system, the SI system. So you can see that we now have in the operation editor here on the bottom a heat transfer express operation, and this is our graphics window here, and then we have an input tree here that we work our way through using the next button, and at every page of this we'll be inputting data. So the first thing to do is look at, we're going to be modelling the whole part. We're going to be looking at a transfer through air, and now for the heat transfer express and forming express operations, we have these sliders to determine how complex and how accurate the model will be, and so this changes things like the mesh and the time stepping. So we're going to look at a moderately simple and a moderately fast simulation because we're just looking at a demonstration here. So we click the next button. In this case, we're not going to model the dies, we're just looking at the workpiece transferring through air, so just one workpiece. And we're going to keep this default, so we're going to look at a steel forging. So we're going to have the workpiece initially from the furnace all at 1200 degrees Celsius. Now the next thing to do is to load in the geometry. So I've already created the geometry in my CAD system and exported it to an STL or a surface triangle. So I'm going to bring in this preform STL, and that's brought in the geometry there. So then the next stage is to mesh this. So all this mesh setup has already been defined by the sliders we've used before. So when we click next, it's going to generate the mesh. So a couple of minutes later, we've got a mesh. And you can use these view options up here to change the view to inspect that mesh. So the next step is to select the material for this. So we're going to open the material from the DEFORM material library. And this is going to be a steel, and it's going to be a 4140 grade steel. So this is the American designations, but we also have the equivalent designations down here. You can see when DEFORM has generated that mesh, it's automatically applied a heat exchange with the environment. So all of that green area is going to be losing heat to the air via convection. So that's actually controlled here. So by default, for the transfer we selected before, it's set the environment temperature to 20 and given us a default convection coefficient for convection to still air. The only thing we need to change here is to set that to 5 seconds, because we only want a 5-second transfer. So on the next page here, we're looking at the step definition. So it's going to move at 0.5 seconds. And the next step now is to generate the database. So this writes the setup for this particular simulation to the database ready to run the simulation. When you click Generate Database, it will run through some checks and it will show you in this message window if there's any warnings or errors that are preventing you from writing that setup, so anything that you might have missed or need to go back and change. So we're going to set this whole process up in before we even run it. So if we go back to the operation editor here, we've got this heat transfer, which I'm just going to double click on that and rename transfer. Press enter. So the next thing to do is to add a forming operation. So if we go to forming, this one we're going to look at a 3D forming express. And then we're going to click on this, and you can see that it's currently highlighted orange here, but when we click on this one, we switch to that operation. And you can see it's brought over the workpiece from the previous operation, and it's now saying read from database. So we'll get to that. So again, we're going to look at the whole part. In this case, we're looking at a hot forging. So this is the forming express operation. So we're looking at forgings. We're going to keep those sliders the same because we don't want to change the mesh. The temperature calculation. So here we're going to just calculate the temperature in the workpiece, and we're going to assume that the dies are constant temperature. So we're looking at one workpiece and 2 dies. And now the workpiece, like I said, is read from database, so it's going to read in whatever the end of this simulation is, the state of this workpiece once it's cooled down through air, and bring that into the forming operation. We're not going to have to do any mesh changes for this demonstration. So now we're on the top die, so these have been loaded in by default. So for the top die, we've got a temperature of 150 degrees Celsius, we'll leave that. And we just need to bring in the geometry again. So I've got the top tool. It just takes a couple of seconds to load that in. And then that top tool we're going to have moving down in the -Z direction at 76 millimeters a second. The bottom die we need to also set as 150 and bring in the geometry. So the next thing to do is to position the objects. However, this is sort of in the future, so we don't know the state of this workpiece at the end of this operation. So what we can do in DEFORM is set up a series of scheduled positioning rules. So where this first came in, we actually, in this operation, we're going to flatten it. So we need to move the workpiece from its location that was brought in from CAD. So I'm going to add a rule here. And we're going to offset the workpiece -25 millimeters in the X direction and -100 in the Y direction. So that's going to move it slightly this way and over to here to be flattened. And then we'll remember these numbers to move it back to where the actual impression is for the final forging. And the next thing to do here is to just make sure that when this comes in, the tools are positioned around the workpiece and put into initial contact. So what we can do there, in this case, when we've just got 2 simple dies and 1 workpiece, we can just click Auto. On this page, we've got the contact. And again, this will generate the contact between all those objects at runtime automatically. This preform at the back there is about 25 millimeters. And in this first operation, we'll be going down to about 9 millimeters between the 2 dies. So we're looking at a total die travel of about 16 millimeters. So the next thing to do is set the stopping control for the simulation. So we want this to stop when the dies are about 9 millimeters apart. So for the distance between the 2 objects, we're going to select the top die and the bottom die. And one thing we need to do here is just set some reference points. So if we go back and look at the geometry for the top die, there's a define reference point here. So we just want to say, we look at a single object and select this point here, and then on the bottom geometry we define a reference point, and we're just going to pick any on that flat there. Now see, at the moment the way they're loaded in, those 2 points are in different places, but they're in the Z direction, they're 0 millimeters apart, but you remember with the schedule positioning they'll be separated, and we want the simulation to stop when that gets to 9 millimeters. So for the simulation controls here, we set a number of steps, and we can see DEFORM will move that top die with a constant displacement every step. So we want that in this case to be about 120, so we have a 0.16 millimeter step size. And we want to save a bit more often, so this is the results, how often the results are saved, so we can view them later. So we'll save that every 5 steps. Now when we get to the generate database page, it says database generation is not allowed, and that's because on this operation we haven't run this simulation yet, so we've just done the setup. So we've now completed the setup for this, and now we'll just be adding forming express operation, 3D forming express. And you can see in this case all 3 objects have been brought over, and so all we need to do now is tweak the schedule positioning and stopping controls. Now in the schedule positioning we need to offset that workpiece by this time 25 and 100 to bring it back over that impression, and then we're going to click auto again. We're going to be moving about 8 millimeters, and again we're going to be looking at a distance between the top and the bottom die, but in this case only 1 millimeters, and you can see the reference points are loaded in from the previous operation. In this case I want to again maintain about 0.16 millimeters per step, so that's actually about 1/3 of the element size in this mesh, so I'm going to put that to 60, and again saving every 5 steps. So now we have everything set up. The next step is to go to simulation, and now we can just click run, and we can queue this on a network server, or we can just run it on this computer. So you can see it started to set up the run. So we'll let this finish, and then we'll come back to this when it's finished. So now this is finished simulating, we can click on the post button up here, and we can look at post-processing the results from the simulation. So on this tab we have a step browser at the bottom, so these are all the records within the DEFORM database that have been computed. So we can click all here to view all steps, and we can also use this to select any increment or particular steps that we want. So in this case I'm going to set an increment of every single step, and we can play through the animation here. So if we put on the temperature, for example, I'm going to change that temperature color bar type to temperature to give us something a bit more intuitive. So at the moment it's all at 1200. We can zoom out like this. So you can see it quite quickly went through that transfer process, cooling down by about 100 degrees, and then it's flattened it, and then it's moving through the forging operation here. So one thing about this particular simulation that was clear at the end here is that the preform was probably quite badly designed. So if we look at it using the Z direction here, you can see there's too much material and it's overspilt over the edge of the flash gap. So in this case we'd need to go back and redesign the preform to have less material in this zone so that that doesn't occur. Another thing that we might want to improve about this simulation would be we had some lettering in the tool here, and that's not being resolved by the mesh, so we'd want a finer mesh in that area if we wanted to see how that lettering in particular flowed. But as an overall simulation, the mesh density here is still good enough to get a prediction of things like the tool load, so we can plot that using graph load stroke tool. So we click this and it automatically selects the top die, tons, and we can plot that. And you can see a trace of the tonnage required as the forging progresses. So I'll leave the demonstration there and we'll go back to take any questions. Okay, so I think we've run over there a bit with that demonstration, but happy to answer any questions on that or any other topics James has talked about. I think you can post the questions in the chat. Did you have anything to finish off, James?
Yeah, sorry, I was on mute. I was talking there, so I forgot to unmute myself. Yeah, I was saying that there's quite a few opportunities to use these simulation tools for existing and new processes to look at defect prediction, new product development, troubleshooting existing processes, load optimization, these areas, and the benefits for using the tools can lead to product process innovation, so developing new ideas, changing processes that are difficult to try out, reducing material and tooling development costs is a big driver at the moment. Obviously, optimizing the processes for furnaces, reducing the energy usage as well. So there's a lot of areas that DEFORM can be implemented for manufacturing companies in their application processes. So oh, sorry, I unmuted myself, and yeah. If there are any questions, please ask them in the chat, and we'll answer those.